Magnetic field. In this lesson, we're talking about magnetic fields, the law of magnetic poles, permanent versus temporary magnets, Earth's magnetic field, Oersted's principle, the right-hand rule, magnetism and electricity, solenoids, electromagnetism and electromagnetic induction, Faraday's and Lenz's laws, and lastly, conventional current and electron flow. Some applications of magnetic fields. Maglev trains use magnets to hover the train above the track and propel it forward. Particle accelerators allow us to see the origins of the universe. MRI machines allow us to check on the health of individuals. Speakers and stereos, earphones, and televisions all utilize magnetic fields. Computer data storage, car horns, and motors also utilize magnetic fields. Magnetism facts. Like other forces we discussed, magnetism is another action at distance force, meaning that it works without actually being in contact with the thing that it's working on. A magnetic field is a three-dimensional region of space surrounding a magnet that will exert a force on magnetic objects. Magnetic fields are strongest near the poles. The magnetic field exists around the magnet whether the magnetic field is causing a force or not, so it's there whether you're doing something or not. And electric fields surround charged particles such as protons and electrons. The properties of magnetic fields in magnets. Magnetic field lines point from the north to the south pole and never cross. So you can see from the north, they go out, and they go back in through the south pole. Where the field is the strongest, near the poles, the field lines are closer together. So you can see you have a higher concentration here and here than you do out here. Since substances like iron experience a force when placed near a permanent magnet, the magnet must be producing a constant magnetic force field. So it's not like you need to turn on the magnet. The magnet is always on. So whether you have a magnet that looks like this, or one of the horseshoe magnets with your north and your south pole, they're always on. They're always going to be able to impact an object that can be magnetized, if that object is brought within the magnetic field. Law of magnetic poles. Opposite magnetic poles, north and south, attract, and similar magnetic poles, so north and north, or south and south, repel. So you can see our north and south, that's going to attract, and then our north and north, that's going to repel. Also, if you had a south and south, it would also repel. And you can see that with iron filings. So if you sprinkle iron filings on top or near a magnet, you can see that they're all going to line up according to the magnetic field lines that we discussed prior. So you can see that this kind of looks like this, with the iron filings making it the magnetic field lines. Permanent versus temporary magnets. Permanent magnets create a constant magnetic field due to the orientation of their electrons. So think of a permanent magnet as those horseshoe magnets or as a bar magnet that you might have seen. Those are going to be permanent magnets. They're always going to be on. Temporary magnets are made from ferromagnetic materials, things like iron. They can become magnetized and produce magnetic fields when they're within a strong magnetic field themselves. So if you take your horseshoe magnet, it's always going to have a magnetic field. So that's going to be its north and south. And then if you bring a paperclip near it, that magnetic field produced by the bar magnet is going to create a magnetic field around paperclip as well. So it's going to become a magnet itself. It's then going to give off its own magnetic field, which will allow it to attract another ferromagnetic material. So you could then attach another paperclip to the first paperclip. That second paperclip will then gain a magnetic field. So you'll be able to attach another paperclip to it. When the field disappears, temporary magnets lose their magnetism. So how could you make the field disappear? Well, if you disconnected the magnet from the first paperclip, so let's just say you pulled the paperclips away, all of a sudden that magnetic field would be gone, and these paperclips would lose their own magnetic field, and the paperclips would just fall off to the side. So examples of things that could become temporary magnets would be things like paperclips like I just talked about, iron nails, etc. Anything that has a ferromagnetic substance can become a temporary magnet. Ferromagnetic materials. Some objects like iron, nickel, and cobalt can become magnetized and produce a magnetic field when brought near a permanent magnet. Like we just talked about the paperclips, as long as they're iron paperclips, they can become temporary magnets because they're ferromagnetic materials. Now, Earth has a magnetic field due to the spinning core of molten iron and nickel. So we just talked about iron, nickel, and cobalt. These are materials that become magnetized. Well, if you have a particular set of circumstances, including these ferromagnetic materials, you can create a pretty strong magnet. And that's what the Earth is. The Earth is essentially a very large bar magnet. Now, this is very important because the sun gives off a lot of solar radiation, which is the result of electrons and protons produced by the sun being directed towards Earth. And we can see that here in this yellow right there. These particles would be devastating if they reached us. They'd increase cancer rates, electricity grid issues, etc. But Earth's magnetic field protects us by creating a shield from the solar radiation, otherwise known as solar winds. So their solar winds come in, they hit our barrier, and they're directed around. Now, some of them actually make it in, just based on the field lines, but they don't actually make it to Earth. They just make it pretty close to Earth. Now, when they make it pretty close to Earth, and we're talking 10,000 kilometers above Earth's surface, mind you, but they're relatively close to Earth, they're going to interact with our atmosphere, and they're going to produce these really neat colors that we call the northern and southern lights. Now, the color depends on the type of molecules that they're interacting with. Now, the color depends on the type of molecule they're interacting with. So you can interact with nitrogen, oxygen, etc., and you're going to produce different colors as a result. Now, as I said, this is mainly happening at the poles and at very high altitudes. So our solar winds come in, most of them are deflected, some that aren't deflected make it kind of close, but not close enough to affect us, but close enough for us to observe their effects. A compass. A pivoted magnet will rotate and point north-south because of its interaction with the magnetic field of Earth. So Earth has a magnetic field like a bar magnet. We've already talked about that. The bar magnet of Earth is orientated like it's shown in this picture with the south end facing up and the north end facing down. So what we consider to be the North Pole is actually the south end of our permanent magnet within our Earth, inclined at a slight angle. So it's not straight up and down, it's at an angle like that. We can use a compass to point towards Earth's magnetic North Pole. So what is a compass? Well, a compass is simply a ferromagnetic material. So if we let our ferromagnetic substance spin freely, it would orientate itself according to the bar magnet of Earth. Earth's bar magnet is in the south-north direction, as you can see again from the top picture. So our north-facing side, our red here, is simply going to line itself up with the south end of the bar magnet, which we call our North Pole. So this guy would be north-seeking because it's facing the geographic North Pole of Earth. So from a different point of view, if you like, this ferromagnetic substance would have its North Pole here because it's being attracted to the South Pole on the Earth bar magnet, and it would have its south pole, because again it's its own bar magnet, facing downwards, because it's going to be attracted to the north part of Earth's bar magnet, as you can see there. Oersted's principle. Hans Christian Oersted was a Danish physicist and chemist who discovered that electric currents create magnetic fields. This was the first connection found between electricity and magnetism. Oersted's principle states that whenever a charge moves through a straight conductor, a circular magnetic field is created around that conductor. So you can see what that looks like here. So if a conductor, like a piece of metal or wire, is grasped in the right hand, like you see in this picture right there, with the thumb pointing in the direction of the current, so the current is going to flow up this conductor just like that. The curled fingers point in the direction of the magnetic field. So we can figure out where the magnetic field is going to be based on what is called the right-hand rule. You're grasping the conductor in the right hand, and you're seeing the magnetic field lines using your fingers, connecting magnetism and electricity. Since the movement of electric charges creates a magnetic field, we know that electrons feel the force exerted by a magnetic field. Therefore, a magnetic field will influence electrons in that field, causing them to move. Moving electrons equals current, current equals electricity generation. So we can conclude that magnetic fields create moving electrons, electricity, and moving electrons create magnetic fields. We just saw that here. We have the moving current, it's going to create our magnetic field, and in a similar way, a magnetic field would create the moving current. So they are essentially the same force, just from a different point of view. And since they are the same force, we call it electromagnetism. So we already talked about the right-hand rule for a straight conductor. This is going to be the right-hand rule for a solenoid. A solenoid is simply a coil of wire. The magnetic field around a solenoid has a shape similar to a bar magnet, but the poles stronger than in the middle. The poles are going to be here, and you can see that the poles are stronger because they're going to be more concentrated. Those field lines are closer together than they are out here, similar to our bar magnet. Since we can run current through a coiled wire, we can create a current-induced magnet, otherwise known as electromagnet. Like we talked about here, if we run our current, we're going to create this magnetic field, and that's essentially what we're going to be doing. But instead, we're running our current through a coiled solenoid, which allows us to create a magnetic field like we have shown here. Therefore, we can activate an electromagnet by starting the current, and we can deactivate it by stopping the current. So what's our right-hand rule for solenoids? Well, if a solenoid is grasped in the right hand with the fingers curled in the direction of the electric current, so now our fingers aren't the magnetic field, now the fingers are grasping in the direction of the electric current. The thumb points in the direction of the magnetic field lines in its core. So you can see how the magnetic field is coming out that way and going in that way. That's because the direction of our thumb is up. Our fingers, again, are representing the direction of the current. So the current is running like this, and therefore our magnetic field is going straight up. Electromagnets create a magnetic field by moving electric charges through a conductor that can be turned off by simply removing the source. The conductor is typically a version of a solenoid. So regarding our solenoid, we can increase the strength by increasing the number of loops. So you can see here we have 1, 2, 3, 4, 5, 6, 7, 8 loops. If we were to double that, we would increase the strength. We can also increase the strength by adding something in the middle, a ferromagnetic substance in the middle specifically. So in this case, we added the iron nail. What this does is that it concentrates the core of the field and increases the strength thousands of times. And lastly, we can increase the strength of the magnetic field by increasing the current flowing through the solenoid. So if we increase the current here, then we're going to increase the strength. So let's summarize. Electromagnetic induction is the production of an electric current in a conductor by moving it through a magnetic field. The law of electromagnetic induction explains how we can create voltage and thus current in a conductor due to a change in a nearby magnetic field. So this is very useful as it allows us to create a current without a power source. We can create electricity simply by spinning a magnet near wires. Faraday's law of induction describes how an electric current produces a magnetic field, and conversely, how a changing magnetic field generates an electric current in a conductor. So that's what we were just talking about. So we can create electricity from magnetism, and we can create a magnetic field using electricity. Faraday's law is the basis behind how we generate electricity. No matter what you use, coal, falling water, etc., electricity is generated by getting a magnet to spin near a copper wire. And that's what I was just talking about on the previous slide. This induces a current within the wire, which eventually is sent to your home. So what I'd like you to do right now is pause the video and have a quick look at this simulation. It gives you a good visual representation of what I'm talking about. Lenz's law. When a permanent magnet is pushed into a coiled conductor, the electrons in the coil respond to the magnetic field by starting to move in a particular direction and forming an electric current. Lenz's law states that if a changing magnetic field induces a current in a coil, the electric current flows in a direction that creates an opposing magnetic field. This is consistent with the conservation of energy. You create the current energy by working against the motion. You are transferring your energy via work into the coil to produce electrical energy. So we take a look at the left picture on the bottom. You can see that if we pull a north magnet to the right-hand side, we're going to create an electric current in the wire here that opposes this motion. Now, how does the electric current oppose the motion? Well, the electric current creates a magnetic field that opposes the motion. So that magnetic field, in this case, will want to bring that magnet back towards the solenoid. On the right picture, if we try to push the north pole against the other north pole, that's going to create an electric current in the wires that will create a magnetic field that will try to push the magnet away. So it's going to oppose that motion. So no matter what we're doing, if we are creating a current in a coil by moving a magnetic field, the magnetic field created by that new current will oppose the initial motion. So many rides that utilize free fall take advantage of Lenz's law in order to stop the cart from hitting the ground. So let's take a look at this in action. So you can see the people at the top, they're going to start free falling, and then all of a sudden they slow down just before they hit the ground. So you might think there's some kind of brakes built into the ride, but really it's just taking advantage of Lenz's law. Let's have a look at it one more time. So what I'd like you to do is I want you to think about how Lenz's law can be applied to rides like this in order to stop the cart before it hits the ground. So how does this all work? Well, drop rides contain a large permanent magnet underneath the seats. So you can see here, underneath the seats we're going to have a large permanent magnet located somewhere here. From the ground to about a third of the way up the tower sits a series of large copper strips mounted vertically. Now you can't see it on here, but along this pole, but if this is what it looked like with the ground right there, about a third of the way up, you have these very large permanent magnets mounted on this vertical support pole. As the cart falls, the permanent magnets induce an electric current in the strips as they move past them. The induced current produces a magnetic field that opposes the downward motion of the cart as per Lenz's law. So as the cart drops, and it gets to this point, it's going to create an electric current inside these strips. Remember, these are copper strips. It's just like copper wire. They can have an electric current going through them. So since the magnetic field that created the current is moving downwards, this newly created current is going to create a magnetic field that opposes this motion. It's going to push upwards. So since we have a force down and a force up, the cart slows down. The greater the distance the permanent magnet underneath the seats travels downwards, the larger this upward force gets. Eventually, that upward force is enough to bring the velocity down to zero. What I'd like to do now is stop the video and have a look at number 4. It's another look at the same phenomenon. Maglev trains. Maglev trains utilize electromagnetic induction to suspend trains above the tracks and propel them forwards. Remember, all we need to keep the train above the tracks is a force upwards, and then what we need to propel it forwards is a repulsion force from behind the train pushing it forwards. And we can use electromagnetic induction to accomplish this. Last, we're going to talk about conventional current and electron flow. Conventional current models, what the scientific community uses, is the flow of charges from the positive to negative terminal. So in this case, it's the left diagram here. You can see we have a positive and a negative. In a conventional current, the current is going to flow, in this case, clockwise. To model conventional current, we use the right-hand rule to determine the direction of the current and magnetic field. So in this case, if the current was going to the right, your magnetic field would look something like that, because this would be your thumb. In the electron flow model, we're showing the direction the electrons, not the current, takes. To model this, you use your left hand with the thumb pointing in the direction of the electron flow, and your fingers curling in the direction of the magnetic field. So in this case, we have our thumb pointed that way, and as a result, our magnetic field would look like that. So let's review. Magnetism is an action at a distant force, meaning that its action occurs without actually being in physical contact with the object that it's acting on. Magnetic field lines point from the north to the south pole and never cross. Opposite magnetic poles attract and similar magnetic poles repel. Magnetic fields create moving electrons, electricity, and moving electrons create magnetic fields. Electricity and magnetism are the same force from a different point of view, and electromagnets are magnetic fields created from moving current. And that concludes our lesson on magnetic fields.